Hello friends, today we will discuss inductance of a solid cylindrical conductor. As we know, in power system, power flows from generator to load through transmission lines. So it is important to discuss the parameter of this transmission line. Like there is one very obvious parameter. If we have a transmission line, that is conductor, it will have some resistance. So this is very obvious, and due to this resistance we will have transmission losses. Transmission loss due to resistance in conductor. There is one more factor due to which we may have transmission loss, that is corona. Okay. So apart from resistance in the conductor, we may have inductance. Inductance is not responsible for transmission loss, but it does have some effect. That effect we will study later. So we have resistance, inductance, and when we will discuss high voltage line which carries power on high voltage, in those lines we will have to consider capacitance of lines also. So apart from resistance, we will have inductance and capacitance in the line. So in the coming lecture, we will be studying how to calculate inductance and capacitance of line. In the present lecture, we will study, most of the conductors are cylindrical conductor. So in the present lecture, we will be studying how to find out inductance of a solid cylindrical conductor. Okay, so to find out inductance of a solidly cylindrical conductor or of any conductor, let us first discuss what is the method to find out inductance. We have done some question while studying transformer with that. So let us have a look how to find out or how to calculate inductance of a conductor. Let's say we have a ring. This is a core material, the dashed part is core material, and the end turns are wound, and let's say we have a current I here. Okay, we have to find out inductance of this winding and core system. Okay, the inductance is independent of the current flowing into the winding. So whenever we will calculate inductance, it will be a property of winding and core system. Okay, so to find out what are the steps to find out inductance? The total flux linkage, total linked flux, this is equal to L into current in the winding. So inductance will be total linked flux divided by current. So let's say I current is flowing into the winding. The MMF will be, we have done this type of question while studying transformer. I am just revising this question. MMF will be total number of turn into current. First I am finding MMF, then flux will be MMF divided by reluctance. Reluctance is total length of the core divided by permeability of the core material divided by area of this cross section in which the flux has been set up. So after finding out flux, what we will do? We will find out the total flux linkage. If phi flux is set up in this core and we have n number of turns, so the total flux linkage will be number of turns into flux. Okay, so the total linked flux will be N, and value of flux is Ni divided by reluctance. Hence L will be total linked flux divided by I. So when we will divide by I, L will be N square divided by reluctance. Okay, so the method for calculating inductance is find out the total linked flux and divide it by the current. So we will adopt the same method to find out inductance of this solid cylindrical conductor. Let's say this is a section of current carrying conductor, and this is the front view. If you will look from this side, it will be a circle, and this conductor is carrying a current I. Here we have to find out total flux linked to or linking with the conductor. Actually, what will happen here? We will have a current into the conductor. Due to this current, we will have a magnetic field. Let's say current I is flowing in this conductor. So due to this current, we will have a magnetic field. Okay, this way we will have magnetic field. So if this is conductor, these magnetic fields are outside the conductor. But here I have represented this conductor with a line only. But if the conductor is cylindrical, apart from outside magnetic field, there will be field inside the conductor also. So the whatever flux is linking through the conductor, it can be divided into two parts: the flux which is linking inside the conductor, and the other flux which is linking from outside the conductor. The conductor is carrying current I, and due to this current only, there will be magnetic field, hence flux, and the same flux will link with the conductor. Okay, so as I said, this flux can be divided into two parts. This will be equal to total flux linking inside the conductor plus flux linking outside the conductor. Okay, so let us try to find out the total flux linking inside the conductor first. Okay, we have to find out total flux linking inside. For this we will first calculate flux inside the conductor, and then we will see how much part of this flux is actually linking with the conductor. For calculating flux, you must have magnetic flux density, and magnetic flux density is nothing but permeability into magnetic field intensity. Okay, so now let us calculate magnetic field intensity. Actually, the magnetic field intensity will not be constant inside the conductor, so we will apply Ampere's circuital law to find out magnetic field intensity at a distance x from the center or from the axis of the cylindrical conductor. Let's say this distance is x. Actually, the magnetic field intensity will depend on x. So instead of h, I will represent it as hx or bx. So what is Ampere's circuital law? Ampere's circuital law is h dot dl, the line integral of the magnetic field intensity is nothing but current enclosed by this surface. Okay, so if current is going inside, the direction of magnetic field intensity will be this, anti-clockwise. So if this is h and let's say this is dl, so for each part of this periphery, what will be h dot dl? Direction of h and direction of dl is same, so angle between h dot dl is 0, so this will be simply h dl. Okay. And due to symmetry, each point is at equal distance from the x. Each point is from equal distance from x, so due to symmetry at each part of this periphery, h will be same. So h can be taken outside the integration, and integration of dl will be 2 pi x. Now what is the total current enclosed by this surface? Total current I is carried by this conductor. The total current carried by the conductor is I. That is, if we consider this cross-sectional area, let's say the radius of this cross-section is small r. This radius is small r. So the total current carried out by the cross-sectional area pi r square is I. So total current carried by unit area will be I by pi r square. And what is the area enclosed by this periphery? This area is pi x square. So the total current carried by pi x square cross section will be I divided by pi r square into pi x square, that is I x square divided by r square. This much current is carried out by this peripheral, by the cross sectional area enclosed by this periphery. Okay, so the total enclosed current will be I x square divided by r square, where I is the total current. So now what will be Hx? The magnetic field intensity at a distance x from the axis of this cylindrical conductor. This will be Ix divided by 2 pi r square. Now what will be B? Bx will be mu into h, and the mu of the conductor is, let's say mu of the conductor is same as mu of air, it is mu naught. So B will be mu naught Ix divided by 2 pi r square. There is one also important thing that I missed while calculating the total current enclosed by this area. Total current enclosed by this area was Ix square divided by r square. While calculating this, I have assumed that the current is uniformly distributed throughout the cross-sectional area. Let us again calculate it. The total current carried by this conductor is I. So current density will be I divided by pi r square. Okay. Now the current carried by the total current enclosed by a periphery of radius r will be J into its area, that is pi x square. So in this calculation I am assuming that J is constant. Okay, in this calculation what I am assuming, J is constant, but actually when a conductor carries an AC current, most of the current tend to flow through the outer section of the conductor, making the current density non-uniform. In actual case, when AC current flows through a conductor, most of the current tend to flow through outer part of the conductor, making the current density non-uniform. If that is the case, we cannot apply that formula. But for the calculation of inductance, I am assuming that current density is uniform. When it makes the current density non-uniform, it is called skin effect. So in one sentence I can say that for calculation of inductance only, I am ignoring the skin effect. Okay, so this is Bx. Now we have to find out flux. Flux is nothing but magnetic field into area. Okay, and what is the direction of magnetic field? This is the direction of magnetic field. This way magnetic field will be set up. Again there will be another line of flux. This way we will have magnetic flux. At a distance x from the center, we have magnetic field intensity and magnetic flux density. So if this is the line of flux, what will be the cross sectional area? This will be a cross sectional area, or this will make a cross sectional area. Here in this diagram, what will be cross sectional area? Magnetic field is like this. Okay, this will make the cross sectional area. Actually, the magnetic field is like this, and it will not only be confined to this surface. This will be throughout the conductor this way. Okay, so the area in front of this magnetic field will be, the two dimension of the area will be, there is this one thickness, and the another dimension is length of the conductor. Okay, and since the flux is dependent on the distance from the center x, I am considering the small thickness dx, and let's say length of the conductor is L. So the area or the elemental area, this will be L into dx. Okay, since the direction of magnetic field is like this, anti-clockwise, since the direction of magnetic field is like this, the two dimension for the area will be, the one dimension will be this dx, and the other dimension will be length of the conductor that will go inside the board. So the elemental area will be L into dx. So the flux will be, why I have considered elemental length, because the magnetic field intensity is dependent on x, so this is a variable. But for the elemental length, I can consider this bx to be constant. So flux will be mu into hx. Mu into hx is Ix divided by 2 pi r square into area is L into dx. But instead of total flux, we will calculate flux. Instead of total flux, we will calculate flux per unit length of the conductor. Hence, in the final result, we will be calculating inductance per unit length of conductor. Okay, so what will be flux per unit length? Let's say this is phi dash total flux. Now I am representing flux phi as flux per unit length. So flux per unit length will be mu naught Ix divided by 2 pi r square into dx. So this is the flux that is set up in this area only. Okay. The area made by this part from radius x to dx, and the length is L. Now we have to find out flux linking through the conductor. This is the flux set up in this area. Now here it is important to understand the difference between the flux linked, or lambda, and flux. Lambda is nothing but the total flux linkage is the number of turn into flux. Now in this case, we have to find out the effective number of turns through which this flux, the calculated flux, is linking. This flux phi encloses only this much cross sectional area of the conductor. Okay, if this flux was linking the whole cross sectional area of the conductor, we would say we have effective number of turn as 1, and in that case we would say total flux linkage will be phi. But here this flux, the flux that is confined between this area, this flux encloses only a fraction of the whole conductor. And what is that fraction? What is the fractional cross sectional area? the fractional cross sectional area is pi x square divided by pi r square, that is x square by r square. So in a way we can say that overall the total number of turn is x square divided by r square, because only this much fraction of total conductor is being enclosed by the flux, or effectively we will say this many number of turns is being linked with the flux phi. So the total flux linkage will be mu naught I x divided by 2 pi r square into x square by r square dx. So this is total flux linking with the conductor, and where is the total flux? This flux is between x to x plus dx, but we have to calculate the whole flux, that is starting from 0 radius to r radius. So that will be, this will be elemental flux. So the total flux will be integration of elemental flux from radius 0 to r. So lambda will be mu naught I divided by 2 pi r to power 4 x cube dx from 0 to r. This will be nothing but total flux linking inside the conductor due to current, due to its own current I. Okay, so lambda will be, here we will have r4 by 4 mu naught I divided by 8 pi. So the total flux linking inside the conductor due to its own current will be mu naught I divided by 8 pi. So this is only a single part of the total flux. Now in the other part we have to calculate the total flux outside the conductor, which is the total flux outside the conductor. Okay, the total inside flux is mu naught I divided by 8 pi. Unit will be Weber. The unit of flux is Weber. Total flux linkage is flux into number of turns, so Weber turns, and we are calculating all the parameters per unit length, so we have a per meter here. For calculating the total flux outside the conductor, let us assume a distance x from the center of the cross section. Let's say at this distance x. The procedure will be same. Let's say this distance is x. First calculate magnetic field intensity, then magnetic flux density, then flux, and then flux linkage. And in this case we will remain outside the conductor. So what will be h? For calculating h, again we will write h dot dl integration. Close integration will be current enclosed. So if we are outside the conductor, it does not matter what is the distance from the center, as long as you are outside the conductor, the total current carried by the conductor will always be I. So here we will have h into 2 pi x will be I. So hx will be I divided by 2 pi x. So b will be mu naught I divided by 2 pi x. Now let us try to calculate d phi, the elemental flux. Okay, since the value of flux is nothing but b into a, but this formula is applicable only when b is constant. But here B is dependent on x, so instead of this formula we will apply d phi is equal to B into dA, or phi is equal to integration of B dA. So what will be dA? Let us consider a width dx, okay, and this length will here we have an elemental width dx, and this length is L. So again the total area will be dA will be length of the conductor into dx. So the elemental flux which will be confined in this area will be B into L dx, or the elemental flux per unit length. Per unit length will be B dx, and B is mu naught I divided by 2 pi x dx. Now what will be flux link, what will be the flux which is linking through the conductor? Since conductor is enclosed by this area, whatever is the flux confined in this area will also be linking through the conductor. So in this case there we will have total flux link per unit length will be d phi. So this is nothing but d lambda. This is equal to d phi. What is d phi? The flux linking in the area L dx only. Okay, that is from radius x to radius x plus dx. So what will be the total flux linkage? Total, which is outside. So if you want to calculate the total flux from where, starting from obviously radius r and up to where we will have to integrate, for calculating total flux linkage we will have to integrate from r to infinity. So if you will integrate this expression from r to infinity divided by 2 pi x dx, that is mu naught divided by mu naught I divided by 2 pi ln x from r to infinity. Okay, when you will calculate this you will get infinity. Total flux linkage is infinity, and this will not give you any conclusive results. Okay, so instead of finding out total flux, let us find out total flux which starts from obviously from radius r and which is confined between radius r and a radius, let's say d. Okay, in the side view let me represent as this. Let's say this is current carrying conductor, this is radius r, and let's say this is distance d. So I'm making a cross section. This is conductor and this is outside the conductor. Imagine the cross section. This will make the cross section. Up to here the distance is r and this distance is d. So in this cross section let us try to find out the flux in this section which is enclosing the conductor, or the flux linking through the conductor between radius r and radius or distance d. So instead of finding out total flux, let us find out the total flux between r and d, and I will represent this flux as, let's say just for time being I am representing it as RD, from r to d. So we will integrate it from r to distance d. So what we will have here, ln x from r to d. This will give you mu naught I divided by 2 pi ln d by r. So this is the total flux between this area and enclosing the conductor or linking the conductor. Okay, so now if this is the outside flux, and what is inside flux? Mu naught I divided by 8 pi. Now if I ask you a question, now what is the total flux starting from the axis of this conductor? What is the total flux linked through this conductor starting from origin or starting from axis to distance d? This will be summation of inside flux and outside flux. So the total flux up to a distance d, which is linking with the conductor, is the inside flux mu naught I divided by 8 pi plus mu naught I divided by 2 pi ln d divided by r. Mu naught is nothing but 4 pi into 10 to power minus 7. So this will be I into 1 by 2 plus 1 by 2 into 10 to power minus 7 plus 2 into 10 to power minus 7 ln d by r. I am taking 4 common. Oh, not 4 common, I am taking this part common. 2 into 10 to power minus 7. So here what we will have 1 by 4 plus ln d by r. 2 into 10 to power minus 7 into I. Let me again come back to the derivation for the outer flux. The result was mu naught I divided by 2 pi 1 by x dx, okay, for this part only. Okay, and what we have calculated here, the flux linked between r and d. It is not necessary, it is not always necessary to find out the total flux between r and d. In fact, you can calculate between any 2 points. Let's say from this distance d1 another distance d2. So the total flux linked or confined by the area from d1 to d2. So in that case we will integrate it from d1 to d2. So it is not necessary to always integrate from r to any distance d. Okay. Here we will have 2 into 10 to power minus 7 into I. 1 by 4 can be written as ln e to power 1 by 4 plus ln d by r. 2 into 10 to power minus 7 into I ln d divided by, when it will come into denominator, first these two terms will be multiplied because we have log. So we will have e to power 1 by 4 into d by r. When you will take this part to denominator, this will give you e to power minus 1 by 4 into radius. And value of this quantity is 0.7788. So the total flux linked between d and r is 2 into 10 to power minus 7 I ln d divided by 0.7788 r, and I will represent this quantity as r dash. The total flux linked will be ln d divided by r dash. So if this is total inductance, if this is total flux linkage, This can be written as inductance into the total current carried by inductor. And what will be this inductance? Inductance only due to the flux D and R. Okay, this is, since this is not the total flux, if we were to calculate the total flux, we would integrate. In the integration part, we will start from R and we will go up to infinity. But since we are not calculating the total flux, we are calculating only the flux which is starting from R and D. This will not give you the total inductance. Okay, this is inductance due to this flux only. That's why I am representing it as LDR. This is 2 into this quantity will be equal to this quantity. I and I will be cancelled. So LDR will be 2 into 10 to power minus 7 ln D divided by R dash. So in summary, what we did, we first calculated the total flux linking to the conductor, the total inside flux which is linking to the conductor, and that is mu naught I divided by 8 pi. Then we calculated total flux. We tried to calculate the total flux outside the conductor, and we got infinity as a result. Okay, so with this result we cannot draw any conclusion. So instead of calculating the total flux, we calculated lambda d1 d2, that is the flux which is confined between distance d1 to any distance d2. This is radius r. Let's say this is point d1 at distance d1. Let us represent the distance with a small d, and this is d2. So make a circle with radius d2, make a circle with radius d1, and between this area, the area enclosed by radius d1 and d2, in this area only the total flux linked will be 2 into 10 to power minus 7 I ln d2 by d1. And corresponding to this flux only, we will define L d1 d2. This will be 2 into 10 to power minus 7 ln d2 by d1. Here we are although when we will have two conductors and we will have to see the effect of, or the total flux linked by second conductor to the first. We will be, although we will be interested in calculating the total flux, this result, in that case also this result will be useful. Although this result does not give the total flux, yet while calculating the total flux or while analyzing the effect of one conductor over another, this result will be useful. We will see it later. We have L d1 d2, or simply L12. This is equal to 2 into 10 to power minus 7 ln d2 by d1. Okay, so now let us calculate inductance of two-wire system. The first wire, in which we will have incoming current, and in the another wire we will have the return current. All, if this current is I, this current will be minus I. Let us now show the direction. Here we will have current I, here we will have current minus I. Let us draw the cylindrical conductor. It has a current I and it will have current minus I. In any system, the summation of total current will be 0. Even in three-wire system, where we have current, in a balanced three-wire system, IA plus IB plus IC equal to 0. I am first considering two-wire system. Okay, so let's say in this system we have to find out inductance of this conductor Lx, and how this will be calculated. If we are able to calculate the total flux linking to this conductor, psi total linking to this conductor due to its own current and due to the current in the other conductor. Okay, as we saw in previous section, if we are required to, or if we are interested to find out the total flux linking to this conductor with its own current, that this tends to infinity. So let us not calculate that. Let us first consider a point P here, okay, which is at a distance, let's say this distance is d. So let us try to calculate the total flux linking to this conductor between point P and its axis. So this we have already calculated. Lambda is nothing but 2 into 10 to power minus 7 ln. Let's say this distance is d, or let us represent this distance. Let's say this distance is from this conductor is x and this conductor is y. So let us represent this distance as dpx, the distance of point P from the conductor x, dpx divided by r dash. So this is the total flux linking with first conductor due to current in first conductor only. Okay, but this will not be the total flux. That in the total flux there will be effect of current in the second conductor. So let us now try to find out the flux linking to conductor x due to this conductor. So how can we calculate this? For this conductor, for the conductor y, the conductor x is placed outside this. Let's say this distance is dxy. So if I ask you to find out total flux due to the conductor y, which starts from the conductor x and goes up to point P in a region or in a circular region, what is the total flux enclosed by the second conductor y, which starts from the first conductor and goes up to point P? We have already calculated this result as 2 into 10 to power minus 7 ln. This whole distance, this distance will be, let us represent it as dpy divided by this distance dxy. In the previous section what we have studied, let's say this is the cross section of a wire. This is point d1, this is point d2. So what will be the total flux linking, what will be the total flux linking with this conductor between d1 and d2? This is 2 into 10 to power minus 7 ln d2 by d1. So this is what I have done here. The total flux linking to this conductor between conductor x to point P will be 2 into 10 to power minus 7, this whole distance, this is at the place of d2, divided by the distance between the conductor and first point, the distance between the conductor and the first point, that is dxy. Okay, so this is the flux linking to conductor x due to conductor y. Yes, I have started from this conductor and I have gone up to point P. Now we have only calculated the total flux linking up to point P. So what will be the total flux? The total flux linking to conductor X due to its own as well as due to its own current and current in conductor Y. So we will have to add these two parts. I have missed current I. Here we will have current minus I. Okay, and here we will have current I. So we will have 2 into 10 to the power minus 7 into I ln dpx divided by r dash minus ln dpy divided by dxy. dpy represent distance of point P from second conductor, dpx is distance of point P from x conductor, and dxy is the distance between these two conductors. So this is the expression if we confine ourselves up to point P only. Now let's say we are interested in finding out the total flux linking to this conductor X. So where this point P will tend to? If we are interested to finding out the total flux linking to this conductor, this P will tend to infinity. Okay, so if P point will tend to infinity, okay, let us simplify it one step, for one more step. 2 into 10 to the power minus 7 into I, this will be ln dpx into dxy divided by r dash into dpy. Okay, now if P point will tend to infinity, can we say that the distance dpx will approximately be equal to distance dpy? Let's say this distance is 1 meter and P is at point infinity, so we can say that approximately the distance of the point P between conductor X and conductor Y will approximately be same. So in that case dpx and dpy will be cancelled out, and here what we will have? We will have the total flux linking to the first conductor starting from this conductor up to infinity. So here we are calculating total flux, although the formula is derived for only for partial linking flux. But here since we have two conductors having current in negative direction, so the term which was responsible for making the whole part infinity, that was the distance term, and this term has been cancelled out here. So here we will not get results as infinity. So the total flux will be 2 into 10 to the power minus 7 into I, the distance between the conductor divided by r dash. R dash is nothing but radius of this conductor into e to the power minus 1 by 4. So what will be the total inductance now? Simply divided by I. So the total inductance of conductor X will be 2 into 10 to the power minus 7, distance between the conductors divided by r dash. So although we did not have formula for total inductance, when we tried to find out the total inductance, we got the infinity result. But for two-wire system, we can find out the total inductance, and the same value will be for second wire also. Now let us calculate for three-phase line, inductance for three-phase line. which are equally spaced, which are equally spaced. And equal phase spacing also, that is balanced current is flowing in those conductors. So if they are equally spaced, they will be in the form of equilateral triangle. Let's say d is the distance between the conductors. Let's say it is carrying current IA, IB and IC. So the summation of these three currents will be IA plus IB plus IC will be 0. And let's say we are interested in finding out inductance of the total inductance of wire A. So again we will consider a point P, because we don't have formula for finding out total inductance. We will consider a point P. Let's say here is the point P. The distance between point P and conductor A, I will assume it is dPA. Similarly dPB and dPC. So what will be the total flux linkage to conductor A, or what will be the total flux linkage up to point P and which links with conductor A? Total flux linkage, this will be 2 into 10 to power minus 7 IA ln dPA divided by R dash, where R dash will be radius of conductor A into e to power minus 1 by 4. So let's say this is flux linking to conductor A between point P okay. Phi A PA means flux. This A is for flux linking to conductor A. This A is for due to its own current, and P is for between P and its axis, the flux in this region. Similarly, flux linking to A between P and B. Let's say P point is here. That is P point. So to calculate flux due to conductor B, which is between point flux due to conductor B, which is between P and A only. This is the conductor B. This distance will represent dPB. So with this radius we will make a circle, okay, and with this distance, let's say this is DAB, with this distance we will make a circle with center at B only. Center has to be at B, and from here we will make a circle, and whatever is the flux, the total flux in this region, this flux will represent phi A PB. And for this flux we have formula 2 into 10 to power minus 7 ln d2 divided by d1. So d2 is distance dPB divided by distance, this distance is DAB, the second distance divided by first distance DAB. Similarly, flux linking to A due to current in C, which is confined up to point P. We are not calculating total flux. All these flux are confined up to point P only. Ln dPc divided by dAc. Okay, so what will be the total flux which is linking to A? Summation of these three flux, and obviously current IB will be here and current IC is here. So 2 into 10 to power minus 7 IA ln dPA divided by R dash plus IB dPB divided by distance. Here we will have AB. So what will be distance DAB? Let's say these are equally spaced, so let's say the distance is capital D. So DAB will be capital D plus IC, and we will have ln also, ln. The third part is dPc, the distance of conductor C from the point P, divided by dAc, distance between conductor A and C. This is again capital D. Now for calculation we will use IC is equal to minus IA minus IB. So here we will have 2 into 10 to power minus 7. At the place of IC we will have minus IA and plus minus IB, minus IA minus IB. So first minus IA ln dPc by D minus IB ln dPc by capital D. Take the terms with IA together. So this will be 2 into 10 to power minus 7 IA ln dPA, and due to minus, this dPc will go to denominator, capital D will be numerator, R dash dPc plus IB into, here we will not have D dash, D only, ln dPB divided by D, and capital D will be in numerator and dPc will be in denominator. Okay, now again, now if we are interested, the total flux linking to the flux A, sorry, the total flux linking to conductor A, which is starting from its radius and going up to infinity. Okay, so where this point P will tend to, this point P will tend to infinity. So if this P point is at infinity, the distance of point P from conductor A and the distance of point P from conductor B and the distance of point P from conductor C will be approximately be equal. So dPB dPc will be approximately equal, dPA dPc will be approximately equal. D and D will again be cancelled out, so here we will have ln 1 that is 0, and here we are left with lambda A will be 2 into 10 to power minus 7 ln D divided by R dash only. And when you are interested to find out flux linking to conductor A from up to infinity, you just have to move the point P to infinity. Okay, so for two-wire system, this is lambda, and inductance will be just divided by current. So inductance will be 2 into 10 to power minus 7 ln D by R dash, and the same inductance we got when we calculated for two-wire system. This is for three-wire balanced system. Okay, and same result we got for two-wire system. Now in this derivation only, let us assume that the summation of total current will always be 0. IA plus IB plus IC is equal to 0, but let us not assume that the distance they are in a space, they are placed symmetrically, or let us not assume that distance between each conductor is d. Let's say these distances are, this is DAB, this is DAC, and this is DBC. Then what will be the change in our result? Okay, so this is same, this will be same, dPA by R dash, here dPB by DAB, dPC by DAC. Up to here no changes are required. Now while calculating lambda A, due to all these current in all these three conductors, what we will have? IA dPA by R dash, dPB by DAB. Here we will have DAB. Okay, and here DAC. Okay, so this will, here we will have DAB, and at the place of IC I have put minus IA minus IB. So this DAC will be same. Here we will have DAC, here also DAC. I am trying to get little bit generalized result. When summation of current is 0 and we have three conductors placed unsymmetrically, so the flux up to point P, flux linking to A up to point P, due to all these three conductors will be 2 into 10 to power minus 7. This will be IA ln dPA into DAC divided by R dash plus IB ln dPB into DAC divided by DAB into DPC. In the first part, IA and IA, so dPA into DAC, and this DPC will come in denominator. Again, if you want to find out the total flux, P will tend to infinity. So let me represent it as phi lambda A total, P will tend to infinity. So these two terms will be cancelled, these two terms will be cancelled. So the total flux we will get IA ln DAC divided by R dash plus IB ln DAC divided by DAB. I think this is not a very useful result. This does not lead to any conclusion. Okay. Now in case of composite conductor, what we may have, for incoming currents, instead of one conductor there may be many strands of conductors. Okay, there may be many conductors which collectively carries a current I. Similarly, for returning current there may be many conductors. Okay, for incoming current, let's say to name these conductors, let us, these conductors are X and these conductors are Y. Okay, they may contribute equal part of the total current I, or they may have unequal current. Similarly, for returning current they may have equal or unequal part of current minus I. So for this type of conductor I am going to write the general formula. The general formula for calculation of inductance X, the total inductance due to these conductors. These inductance will be 2 into 10 to power minus 7 ln GMD divided by GMR. GMD is geometric mean radius, geometric mean distance, and GMR is geometric mean radius. Okay, so for calculating inductance of conductor X, this will be a composite conductor. You can calculate with the help of this formula. So while calculating inductance, the only trick is how to find out GMD and GMR. Let's say we have to find out inductance Lx. So for calculating GMD, let us try to calculate distance between each strands of conductor X and each strands of conductor Y. How many distances we will have? Let's say for this strand we will have 3 distances. Let's say this is 1, this is 2, this is 3, this is 4. 4 strands. Similarly in Y, this is 1 dash, 2 dash and 3 dash. Now let us take distance between strands of this X conductor and Y conductor. So the first distance may be distance between first strand of X conductor and first strand of Y conductor. So the first distance will be 1 1 dash. Similarly second distance will be 1 2 dash. Third distance will be 1 3 dash. Okay, so from first conductor we have 3 distances. Similarly from second conductor of second strand of X conductor to this will be 2 1 dash, 2 2 dash, 2 3 dash. Similarly for third strand of X and fourth strand of X. So in total we will have how many distances? 3 for each 4, that is 12 distances. So first in the root we will have 12 here, and now multiply all these all these distances. D 1 1 dash, D 1 2 dash, D 1 3 dash, and so on. So this way you can calculate GMD. For calculating GMR, we will have to confine in X part only. And to find out GMR, what we will do, think of first conductor, the distance of first conductor from second, distance of first conductor from third, distance of first conductor from fourth, including its R dash. I have already discussed what is R dash, R into e to power minus 1 by 4. So for first conductor only we will have 4 type of distances. Okay, I will represent it as R11. This will be R12, R13, R14. Similarly we will have R dash 21, R21, R22, R23, R24. Similarly for third and fourth, we have 4 type of distances for each 4 conductors, and if you will multiply, you will have here 4 into 4 and all the distances. So this way we can calculate GMR. So this is a very general formula, and only the tricky part is to find out GMD and GMR. Let's say this is conductor Y. In only one conductor there are 2 strands, where only in one conductor we have 3 strands. 1 2 3. This distance is 0.5 meter. This is 1.5 meter, and the radius Rx is 0.03 meter. Here radius is 0.04 meter and the distance between the strands is 0.3 meter, and this distance is also given as 2 meter. And we have to calculate Lx and Ly. Okay, Lx and Ly. So for calculating Lx, the formula will be 2 into 10 to power minus 7 ln GMD divided by GMR of x. For calculating Ly, we will have 2 into 10 to power minus 7 ln GMD will be same because it is between x and y divided by GMR of y. Okay, so first calculate GMD xy. For calculating this, how many distances we will have? For calculating GMD, we will take distance between x and y, distance between each strands of x and y. So for this strand we will have two distances. The first distance will be, this is 2 meter and 2 meter. Distance between 1 and 1 dash, B11 dash, this will be 2 plus 2, 4 meter. D12 dash will be 4 plus 0.3, 4.3 meter. D21 dash will be 4 minus 0.5, 3.5 meter. D22 dash will be 1.5 plus 2, 3.5 plus 0.3, 3.8 meter. D31 dash will be 2 plus 0.3, 2.3 meter. D32 dash will be, D31 dash will be 2 meter only, and this distance will be 2.3 meter. So these 6 type of distances we have. So we just have to multiply these distances and just multiply these 6 distance, and to the result do 1 to the power, we will have 1 by 6 here. So this will give you 3.189 meter. 3.189 meter. This is GMT. To calculate GMR, we will have 3 distance for this, including its radius, 3 for this, 3 for this, total 9 distances. First we will have R11 dash, that is 0.03 into 0.7788. R12 is 0.5, R13 is 2 meter. Similarly, R22 dash will be 0.03 into 0.7788. R, this is not 22 dash, this is R dash. R23 will be 1.5 meter, and R21 will be 0.5. R31 is 2 meter, R32 is 1.5 meter, R33 dash is 0.03 into 0.7788. So we have 9 distances. Multiply all these distances and get a result to power 1 upon 9. So this will give you 0.3128 meter. this will be GMR for X. Similarly, GMR for Y will be, we have only two conductors here, so R11 dash will be 0.04 into 0.7788. R12 will be 0.3 meter. Similarly, R21 will be 0.3 meter and R22 dash will be 0.04 into 0.7788. We have only four type of distances here. Multiply all these and get the power of 1 by 4 to the result. So this will give you GMR for Y. And for Lx we will have 2 into 10 to power minus 7 ln GMD divided by GMRx. This much Henry per meter. Remember, we derived formula for per meter inductance. So 2 into 10 to power minus 7 ln GMD is 3.189 meter and GMR for X is 0.3128. This will give you 4.644 into 10 to power minus 7 Henry per meter. This is Lx. For Ly, 2 into 10 to power minus 7 ln GMD divided by GMR of Y. 2 into 10 to power minus 7 ln GMD is 3.189 and GMR for Y, here if you will calculate, so Ly will be 6.992 into 10 to power minus 7 Henry per meter. And the total inductance of the line will be Lx plus Ly. So this will give you 11.64 into 10 to power minus 7 Henry per meter, or 1.164 microhenry per meter. So apart from the basics, in the calculation of line inductance or inductance of a line, the basic thing is to find out GMD and GMR. In three-phase line, we will have three conductors. Let's say this is for A phase, this is for B phase, and this is for C phase. This way we will have three conductors, and obviously the distance between each conductors are not same. Let's say this is for position 1, 2 and 3. So the distance between position 1 and 2 and between 2 and 3 looks to be same, but to make it general, even let us assume that even distance between 1 and 2 and 2 and 3 are not same. Okay, and obviously distance between conductor 1 and 3 is different. Okay, so in this kind of three-phase line, since the distance between the phases are not equal, since the distance between the conductors are not equal, the balanced positive sequence flux linkage does not occur. Even if the currents are balanced, I have written here equal phase spacing. It means currents are balanced in each phase, or the positive sequence currents are balanced in each phase. The positive sequence flux linkage are not balanced because the distance are varied, and unequal or unbalanced positive sequence flux linkage occur. But these unequal or unbalanced flux linkage can be balanced by interchanging the position of conductors. Let's say conductor positions are changed. So here A is at first position, A is at second position, and A is at third position. So this way balance can be achieved. And for calculation of inductance, the same formula will be used: 10 to power minus 7 ln GMD divided by GMR. So since positions are interchanged, so we will have different type of distance. Let's say we are required to find out inductance of conductor A. Okay, so for calculation of inductance of line A, this formula will be used. There will be many strands. Let's say this is first position, second, third position. This is conductor A. Here conductor A is at second position. Here conductor A is at third position. So there will be some GMR of A. It will depend how many strands of conductor are here. So GMR it may be given, or it can be calculated separately. Actually in transposition we have to calculate GMD. So for calculation of GMD for conductor of phase A, so in this position only, how many distances we have? This is D12 and this is the two distances from phase A. This will be D13. Okay. In this position what we have? This is D12 and this is D23. In this position D31, that will be equal to not D31. This is position 3, this is position 2. So we will have D32, which will be equal to D23. And the another distance will be, you always have to measure from conductor A the remaining two distances. So first distance is this, second distance is D31, that is D13. So how many distances you have? Obviously 6 distances. Take the geometric mean. So D12 into D13 into D12 into D23 into D23 into D13. 6 distances, then power 1 by 6. D12, D12, it is twice. Each distances are twice. So we will have D12 square into D23 square, D31 square to power 1 by 6, that is D12 into D23 into D31. Actually we have only 3 type of distance, so you don't have to do this much of calculation. Only 3 different distances, so multiply these 2 distances and take the geometric mean. This way you can calculate GMD.